So welcome guys, now we are going to mesh our simulation. Meshing our simulation and getting a very good result is it's a challenging mission, and we want to put a very big effort in doing this. Okay, actually, as a VFX artist, you will have a challenging mission of meshing every simulation and getting the balance between the details and the time consumed. But if you are in a studio, you should have a very strong computer, and actually you may have render farms. Okay, but you still have to balance between the details and the crash of the looking of the simulation. Actually, sometimes you try to catch every detail, but you are surprised that the whole mesh is crashed, and the mesh looking becomes strange as you try to change or raise your resolution. Okay, so without further ado, I have loaded the compressed mesh. Okay, after this we are going to convert this to a VDB. Actually, we are going to use VDB tools because they are very fast, and yeah, there are a lot of options to change the shape of our mesh. So the node we are going to use to convert our mesh to a VDB is called VDB from particle fluid. Okay, actually there is a particle separation option here, and we will use the same particle separation as the simulation and the same voxel scale. The influence scale makes our mesh smoother, but it takes a lot of it takes more time to compute. Okay, so lowering this value makes our mesh smoother, but it will take more time. So now we will just drop it to 1.5. The droplet scale, I will keep this to 1.5 for now. I just want you to see something. Okay, so now let me see the result. Oh, I'm sorry, I forgot to unpack this compressed mesh. We still have no points here. This is just a point for each voxel of this compressed mesh and not a real point. So to unpack or uncompress this, we will use the node unpack points, and now we have our mesh, our points unpacked. Okay, so what's your problem? Droplet scale must not, oh, I'm sorry, this droplet scale must not exceed the influence scale. Actually, because this will be messing with something in the computation of the VDB. So you should not set the influence scale to be smaller than or equal to the droplet scale. Okay, so now I have put 0.8. Let me put 0.1 for now. Okay, I will pause the video and I'll see you after it finish. So this is the result, and as you can see, it's very lobulated, and it seems that that it converted our particles just to spheres. And look at this spheric looking here. Okay, this is because we have changed this droplet scale to be very small, and this means the mesh around every particle will be very thin, and this causes each particle to be separated from the adjacent particles, and this causes this spheric looking. So I will set the droplet scale to 0.7, and I hope you now got the idea of the droplet scale. It's just the scale of the mesh around the droplet or around the particle. So the more you increase these parameters, the more thickness and the less separation of the droplets. Okay, so let me set it to 0.7 and see. So now our simulation mesh is smoother, but you still have these separate droplets that we don't need. So if we just see our particles, these droplets here, here and here, are very small, and their number is very big. So they just make our simulation mesh here very noisy, and this doesn't yeah, you don't see the water mesh like this, and it's not full of droplets like this. Okay, so we will just delete these droplets. As you can see, or as you can remember, I hope you can remember that we have used the droplet attribute for the drag, and we called it droplet drag. Okay, so this added droplet attribute can be used now in order to select or delete the high number of droplets here. Okay, so we will just add a plus node, and as you can remember, the more the separation the droplet has, the more value it will be in the droplet attribute. Okay, so this separated droplet here, for example, will have very high, or will have higher droplet attribute than this droplet here. Okay, we will depend on this, and we here in the group field here, we will just enter this expression add droplet. This corresponds to the droplet attribute larger than 0.3. So each particle that has droplet attribute of a value larger than 0.3 will be deleted. And actually we need to set this to points in order to apply this for the points. Okay, and this deletes those separate droplets. Okay, so now connect this to this VDB and see. So now this is our simulation mesh. Okay, and as you can see, the excess number of droplet now is deleted. Okay, our next problem is that we need to get the thickness of the container. So to do this, let me here see press the middle mouse button here. We have the surface field, which corresponds to the surface of our fluid simulation, and our velocity field. Okay, if we just add a blast node here to isolate this surface field here, just select add name equals surface, delete non-selected, and now we just have our surface volume. It's not visible in the viewport, but if we just add a node convert VDB and select this, convert it to polygon, this is our surface field. And I want just this area here, which is the thickness of our container. I want to add it to the volume that we have made here. Okay, so to do this, I want to isolate this area. I want to isolate this area and delete it to just have this container. Okay, so to do this, we have a node called VDB segment by connectivity, and this isolates the connected areas. So this area here is connected to each other, but this rectangular, or this container here, is connected connected here, so it will be isolated from this. So if we just connect this here, and I will select the surface field. Okay, oops, I'm sorry, I will just connect it to the surface field, not the VDB, converted VDB. Okay, so as you can see here, each area is separated in a segment, and each segment is colored by a different color, as you can see. So this area here in the red is connected, and those separate droplets here is the droplets that I don't need. So now we have each area here has a name at surface 0, surface 1, surface 2, blah blah blah. So now I will isolate this this segment, which is called surface 0. So I add another blast node and select surface 0, delete non-selected. Now we have this area here. We want now to delete this color, so we will add an attribute delete, and select in the primitive attribute, select the color. Now we have the surface 0. We need to call it surface only, not surface 0, before we combine it with the with this VDB. So add a name node. Okay, select this surface 0, and the new name is surface. Now we have it called surface. Now I did VDB combine, and this VDB combine allows us to add two VDBs to each other. So we will add this to this. Okay, so here and here, and the operation will be as the F union, and this will just combine the two VDBs. If we see now the result, now if you see the result, they are combined, and we have the thickness here of the container. Now we need to smooth this area of interest here to have better looking. So in order to smooth, we add a VDB smooth node. VDB smooth is the F. Okay, and it will be we will use Gaussian smoothing. This is just a kind of smoothing. And for the values here, we are going to set the radius of the smoothing to 2 and the iterations 2. And actually this is something like the strength of smoothing, and this is the iterations or the number of smoothing. So we were applying the smooth 2 times with this strength or with this radius, but we just want to smooth the area where the velocity is high. And actually we can isolate this area based on the velocity, because the velocity in this area is high, and also the curl. And here I will just have to explain what the curl means. The curl is just the degree of rotation. So whenever you have some vorticity and rotation, turbulent movement, you will have high curl. Okay, so you can just imagine curl if you just put a stick in a turbulent water. You will have this stick rotated, and this rotation is just the curl, and it corresponds to the vorticity of the water. So to compute the curl, we need the velocity volume here from our compressed cache. So we'll isolate the velocity volume and compute its length, which is the speed, and compute the curl from it, and use these two volumes to isolate this area of interest. Okay, so I think you know from your math background that velocity is just a speed with the direction, and if we just need the speed, we compute the velocity length. Okay, so let me do this in order so that you can see it clear. First thing, I will add a blast node, and this blast node I will select the velocity volume. Actually at name equals vel, because each volume has its name stored in the attribute name. So whenever you have a volume or something that has the value of vel at its name attribute, isolate it or delete non-selected. So now we have the velocity. The first thing is to compute the length of the velocity, because velocity is just the speed with a direction. To compute the speed, which is the amount of the or the quality that describes how fast we move without a direction, we need to add a VDB analysis. And in the VDB analysis, we are going to select length. Okay, select the velocity volume, and for the name of the new volume here, I will just call it speed. So now it's called speed instead of velocity. It's called speed. Okay,